Hi everyone, my name is Daniel Marbach. I work for a company called Particular Software, and we are the makers of Enterprise Bus. A very warm welcome from my side from the sunny Switzerland, in the middle of Switzerland, central Switzerland, for the .NET Summit 2020 talk. So this talk is going to be about do-it-yourself and async message pump lessons from the trenches. Before I joined Particular Software, I was working for a consultancy company in Switzerland, and we were tasked to build a patient record system that managed roughly 4 million patient records of patients in Switzerland. It was a huge legacy system that was running on 13 servers, had million lines of code, and it was evolved over time. We actually started around the .NET 1.1 timeframe and continuously evolved the system over time. And one day the customer came to us and said, hey, wouldn't it be cool if instead of just doing medical invoicing type of stuff, we would actually extend the system to do general purpose invoicing. And by the way, I don't have a lot of money, but I'm sure you can make it. We were like, no, not really. Has it ever happened in your project? I'm sure it has. Well, because we knew that we somehow have to address the temporal coupling that we had in our architecture to make it possible to deal with all the web shop that are going to be connected to our system for the general purpose invoicing stuff. And those web shop actually are running 24 hours and not like the doctor systems that were mostly running during business hours. We said, well, we want to leverage a message queuing system to be able to better scale and predict the load and not lose any requests, or even worse, lose the maintenance window. Because like I already said, we are actually, as consumers, we're actually accustomed to web shops being available all the time. So even right now, if you're listening to this talk, you could basically, in parallel to hear me talking, you could open up, for example, your cell phone, browse on your favorite web shop of the day and order whatever fancy thing you want to order, right? And that can be during the middle of the night or during the daytime, it doesn't really matter. Well, we started around a small use case, which was around invoice refunds, and we went to the drawing board and discussed the new architecture approaches that we wanted to choose. We choose a step-by-step approach because we couldn't really afford to microservice the shit out of the system, for lack of a better term, I'm sorry. This is the architecture that we came up with. So we were still using WCF services at the time. We had a lot of Windows services. It was working fine. It was still at that time, it wasn't like the newest technology, but I mean, you probably know it. If you have a million lines of code, you can't just like rewrite everything from one day to another. The WCF services were most of the time actually sending direct requests to the backend services, which then wrote into the database using ADO.NET. And we used the SQL Server cluster to actually store the data. So what we realized was that whenever the refunds came in from all the web shops, what they mostly did is once they actually sent in the refund, they started querying the shit out of the system in order to get to see what happened. I don't know if that's something that is quite common in the PHP world. We had mostly WooCommerce and other PHP platforms connected to our services that were sending in those invoice refunds. Maybe there is some misconception somewhere that people think the more you actually poll a system, the faster the request will be handled. I don't know. Anyway, we needed to address this in some way. So what we did is we essentially, once we got the request on the WCF service, we wrote an invoice refund state into a query cache in the demilitarized zone. Then we created a refund command and put it into a messaging cluster. At that time, we were using MSMQ because it was already available on the Windows service that we were using. The backend system then, whenever it had time, could essentially pick up that refund command or invoice refund command, could do its processing right against the database. And whenever we had some problems with the database, for example, we had huge structures and indexes that weren't entirely optimized we were also working on that. Or for example, when we got transaction timeouts, we were actually able to retry those messages. And then once we had successfully handled those messages, we could then just publish an invoice refunded event back to the queue, which then was subscribed by the demilitarized zone, which then updated the front-end query cache. So what we can say is, well, we had a really good, we had achieved a temporal decoupling of the front end versus the back end. We had really good scaling vectors because we could basically do competing consumers on the queues. We had good throttling semantics. So for example, when the storage cluster could only handle a certain amount of requests per second, that could be controlled by essentially tweaking the consumers on the queue. Like I already said, when something happened wrongly on the database, we could then retry those calls, and we had nicely encapsulated the business transactions that were sent against the stateful middle tier into messages. So we could also say that we had intent capturing requests as messages. So we were like really fully bought into this messaging world. So we had the next tough decision to make once we had this initial architecture thoughts already set up. And the decision were, should we essentially, even though we're using MSMQ, should we essentially write our own abstraction that basically leverages the underlying MSMQ APIs and encapsulates it nicely so that every developer in the team, and we were many at the time, could actually write meaningful business code without needing to worry about the plumbing aspect. So we actually were thinking about, should we build our own messaging abstraction library, for lack of a better word, or should we buy something off the shelf? Something off the shelf could be a commercial product or could also be an open source product where we get professional support services alongside with it. That's why I use the term buy. By the way, in this project that I was talking about, we went for buying a messaging abstraction library, but in another project that was also part of, we didn't, because there we thought, like, after all, building a messaging library can't be that hard, right? Well, let me walk through some of the challenges that we faced in building a robust and reliable messaging library or abstraction, so that you, should you ever be tasked in one of your projects to actually do something like that, you can benefit from the pain points I've already went through and suffered through and lost a lot of hair of it. I'm not sure if you can see it, but I already lost quite a bit. So no, just kidding. It's probably not because of that, but we never know, right? Okay, so but before we do that, we actually have to talk about what are the basic features that we do expect from a messaging middleware. So I took the initial architecture drawing that we did again as an example, and we can see we need in the .cf services, we need something that basically is sending messages to the queue. So what that means is it needs to map the business intent, the message, and hopefully a command or something like that, puts it into a payload, serializes it, and then sends it into the right destination queue. And then on the other hand, in the Windows services, we need something that actually receives the messages, right? So the task of this receiving component, so to speak, has to get the message out of the queue, dispatch the business logic in a safe way, and then eventually publishes further messages, hopefully events, to the destination queue that are subscribed to receive those events. And of course, what's also important is that we require this everything to be safe. Should something go wrong, like I described, that the receiving is actually retried and no messages are lost. Sounds super simple, isn't it? Let's see some basic code. So before we actually see the demo, I would like to show you some basic code in C#.NET using the task parallel library, how a reliable message pump could look like. And that's actually the initial version that we started with. So here on the screen, we see a bunch of C# code. It's quite a lot. Don't worry, you don't have to understand all of it. I will dive into different pieces of the puzzle while explaining it. And I will also share at the end of this talk a repository should you wish to dig further into the pieces of the code. So what we can see here is we have a start method. And in the start method, what we do is we create a cancellation token source. We get the cancellation token, as you probably already know. And if not, I'll mention it here. .NET implements corporative cancellation, which means is the implementer is actually tasked to check whether they can cancel the requests or not. So we fire off a pump task, and that pump task responsibility is to loop until it gets canceled, receive the payload from the queue, and illustrated here by a value tuple containing the payload, which could be a read-only memory or a byte array, and some headers, because usually most queuing systems differentiate between the actual payload and the headers or the metadata, so to speak, that are associated with the messages. And once we get the headers and the payload, we then deserialize the payload and potentially the headers, depending on the format that we're using, into the actual logical payload or the business payload. It could be a JSON deserialization, XML, or whatever format you need to use. And then we execute the business code illustrated by await handle messages. So what I'm showing here a sort of a polling API that basically does long polling over a queue to verify if there are messages in there. Of course, certain type of SDKs that you're going to use provide higher level capabilities or sort of push capabilities, so that you might not need to have this while loop in place, but the underlying SDK does it for you. But it really depends on the queuing system that you're going to use. And like I already mentioned, some SDKs have, and some queuing technologies have, the differentiation between payload and headers, and some don't. And then you actually need to differentiate that yourself and create an additional transport message that deals with that. And that's basically almost all of it. And then here I have the handle message, and here for the sake of this demo, the handle message just does an await task delay of 1,000 milliseconds, and then it outputs something to the console. Good. And last but not least, we have to stop. So what we want to do is we're saying, okay, Once we're stopping, we're giving the cancellation token 5 seconds to essentially trigger a state change, and then we await the pump task to be completed, and then we dispose all the necessary resources. Here it's the cancellation token source. So that's basically all that you need to do to write a message pump that fetches messages from the queue. So the sending part, well, I spent quite a lot of time on exploring the receiving part. The sending part, I didn't really show it because it's pretty straightforward, isn't it? Because we're basically serializing headers and the payload, like we already said. We send it to a destination queue. Somehow we need to map what the destination queue it is, open up the connection, and then send the payloads to that destination queue, including the headers. I will explore the challenges lurking in the sender-side implementation a little bit later. But for now, that's basically all we have to worry about as an illustrative example. So let's recap what we just saw in the previous code so that hopefully you can remember the high-level points after we dove a little bit deeper into the TPL and C# stuff. So what we can say is, with a little bit of TPL hand-waving, some corporative task cancellation 101, and some async sprinkle magic, that we have been able to build a good and robust message pump that really works continuously until something interesting happens. Well, the rush hour. What is the rush hour? Well, in our let's imagine a small web shop out there has this precious item that everyone wants to buy. And then they have some problems. They want to do invoice refunds, or it's even potentially the orders. We're handling the orders over messages. People start buying like crazy, ordering stuff like crazy. And what this code does, let me illustrate it to you with a little diagram. So what we can see is that once a message is in the queue, the message pump takes out that message, invokes the handler, and once the handler is done, it then executes, takes the next message out of the queue, does the spiel, and invokes the handler, and that's it. So what we can see is the message pump that we just wrote handles one message at a time, right? So depending on the execution speed of this code, the queue will start filling up if we have a lot of orders that we receive during the rush hour. So what we can say here is, in the messaging world, we have what it's called the critical time. And the critical time went through the rooftop. What is a critical time? Well, the critical time is the time that is spent between a message being sent and when it's fully processed. And so it's a combination of what we can say the network send time. So that's the time a message spends on the network before it's arriving in the destination queue. Then the queue wait time, which is the time a message spends in the destination queue before it's being picked up and processed. And then we have the actual processing time. So that's the time it takes for the destination endpoint to actually process the message, right? So as a very simple example, we can say is, if the handler time takes 1 second, then the processing time is 1 second. If we have 3 messages in the queue and the 4th message comes in, right, it takes at least 3 seconds until the 4th message will be handled, because the processing time takes 1 second. I now neglected the network send time. Let's imagine it for now, it's 0. So what we can say here is the critical time for the 4th message is at least 3 seconds. And depending on the network send time and other potential latencies, it will be much more, okay? So we said, well, we can address this easily. Let's put our sleeves back and get some coding done. And I will show you the code. But before we dive into the code, I would like you to illustrate what we just saw on the diagram by running the code that you previously saw on the slides. So let's have a quick look. So when we run the first version of the message pump, we can see is we're executing one message at a time every 1 second, and then we are completed. Like we said, we are engineers, we are coders, right? We can solve everything with code. So let's put our sleeves back and let's throw in some concurrency. After all, it isn't that hard, right? Okay, so let's have a quick look what we changed. So this is the new code that we introduced. And again, a bunch of code, probably too much for you to see the details. So I'm going to zoom in right now. But what we can say is we just slightly twisted the previous code. So we said, well, instead of awaiting the actual handling of the message and fetching of the message, how about we just fire and forget the task? Here I'm using this method fire and forget, which is an empty extension method on top of task, but you could also use the discard operator in later versions of C#. For example, the discard example would look like underscore equals fetch and handle message of type of token. And then we are not awaiting the task anymore. So what we can say is, instead of sequentializing the flow, we no longer await it, so we're handling things concurrently. Everything else is the same, and we just have to be careful to log when something goes wrong. And as you can see here on the screen, fetch and handle message does nothing else than just reading, again, the same payload and headers from the queue, deserialize it, handle the message, and the rest is absolutely the same as before. And then we're shutting, when we're stopping, we cancel. This time, I deliberately chose a different value. It's no longer 5 seconds. It's now 100 milliseconds. And you will see why soon in the demo after we did the recap. And then we shut down. So we said, at that time, we said, like, well, since this is just a little change, we don't need to do extensive Q&A. Let's ship it to production. What could go wrong? Well, it worked until this freaking damn rush hour came again. If we only wouldn't be making that much money, right? Life would be so much easier. Oh, wait. We're actually losing money right now. How is that even possible? Well, what we can say is the pump runs with unbounded concurrency right now. So theoretically, until the message queue starts throttling us, the pump is picking us up as many messages as it possibly can without any limitations. Any limitations, though, is actually a lie, right? Because we know that every system has limitations. Well, for example, the code that we call always has limitations unless it's specifically built to not have limitations. But for example, if you're doing regular database calls, the code that gets invoked by the pump at some point in time might be depleting the connection pool resources and start running into weird database and transaction timeout issues due to overloading the database. And once that happens, we lose all the benefits we introduced with the storage-based queues in the first place. Remember, we could have used in-memory queues, but then we have no possibility to scale the queues independently from the process that consumes the messages from the queue. And plus, the process can then grow basically indefinitely in terms of resource usage. So with a file-backed queue, the queuing capability has different scaling vectors in place. But once we start consuming the messages in an unbounded way, all bets are basically off, right? Because the weakest link in the chain, in this example, it is the database, will basically fall apart due to missing throttling. I know I'm deliberately unfair a little bit here with the database. Right? We know that a lot of database can actually scale quite well, but again, every system has its limits. So for example, the DB connection pool that we have for applications.net might be by default limited to 100 connections. So that means if we have more than 100 messages in the queue, we will try to allocate more than 100 connections, which means we will try to overreach from the DB connection pool, and then all bets are off and exceptions will start throwing, and then we get back throttled in the best case, and in the worst case it will actually crash the process depending on the resources that we are trying to consume, right? So let's have a quick look. And again, I would like to remind you about the 100 milliseconds. So I'm showing you a demo that I ran on my i7 8-core machine. It's already a bit old. It's almost 3 years old. I run it for 100 milliseconds, and this is what I got. As you can see here, is we're now handling multiple 10,000s of concurrent operations at the same time and completely overwhelming my system. And by the way, what I did not mention before, it's not only the queuing system, but it's also the application resources that we're using. Like for example, the thread pool of the .NET applications has a limited capacity, and the more we actually try to get resources from it, the more it might need to ramp up capacity, the more memory we consume, and then we saturate the machine completely, which can also have ripple effects in many cases, like the CPU switching and stuff like that. So overall, potentially the performance will suffer greatly. So, well, we then thought, okay, so well, that was a great lesson. We learned something about concurrency and overwhelming the system. So what if we could actually limit the concurrency so that we can tweak the pump to the weakest element in the chain, the code that is called? For example, again, with the standard DB connection pool size of 100 connections, it would be very nice if we could handle the concurrency and limit to 100 messages concurrently to not overflow or DDoS the system and here the database. Well, we can do that in .NET. There is, for example, a structure called semaphore slim. It's like a traditional semaphore, but way faster. I'm not sure if you're familiar with the term semaphore. As a really brief example, it's basically like a toll booth on the highway. So, for example, if you have 8 lanes of the highway, the toll booth is basically the semaphore because concurrently it only allows to pass through 8 cars at the same time. And the semaphore with 8 slots would act like a toll lane on a highway with 8 lanes. Yes. So let's have a look. So what we can see here is we introduce this tiny little change. So we introduce the semaphore slim. We give it a max concurrency. It can be number of CPUs. It can be 100, for example, if you want to align it with the DP connection pool or whatever resource you have in place. And hopefully it's configurable because it might depend on the process that you're running. And then before we are trying to fetch more messages from the queue, what we do is we do semaphore wait async. So that means if the semaphore still has slots available, the semaphore wait async will not block and it will continue. And then we fire and forget, like before, the task that fetches and handles the messages and releases the semaphore. Right? So that means if we have set it to concurrency 5, we basically fall through 5 times and we will try to fetch 5 messages. And then once we reached once we go the 6th time into this loop and we have already acquired all the available slots in the semaphore, the wait async will hang asynchronously until there are slots available and then kick off again. So this allows us to basically dynamically adjust the rate depending on how many slots we have available in the semaphore. That's a really nice way of controlling the concurrency. So, and like I said, the most important part once we have the semaphore in place is also to determine the piece of the code that actually knows we have successfully handled the process and we can release the semaphore. Because if we don't release, then we will actually starve the process because we will not consume anything anymore, right? The rest is exactly the same, deserializing the payload, reading from the queue, handling the messages and all that stuff that you're already familiar with. Okay, and then for shutting down, because now we have a semaphore in place, we actually want to gracefully shut down potentially. What does graceful shutdown mean? Well, graceful shutdown means we're basically giving time to the loop to complete, but we're also saying, well, in some of the cases, what we want to do is we might want to wait until all the currently ongoing handle operations of messages can successfully complete after a given time. So we're basically saying all the concurrently operating requests that we have or queue fetches can still go on for 5 seconds. And then we gracefully await the pump task. And then we're saying, well, let's idle until all the semaphore slots are available again. And then we know that everything has completed. Then we dispose the resources and we are done with this code. Okay, let's have a look how this would look like in production. So when we run this demo, we can see that we have continuously, I limited the concurrency to 3. We have continuously 3 blocks of pumping coming in, even though we have already scheduled multiple messages into the queue. So we have a deterministic way of handling the messages, and it's no longer all bets are off unbounded concurrency, and we can actually tweak that concurrency to our needs of the application. So that's a really nice way to actually deal with such systems. So as we can say here is that we can use this on the process level, a simple semaphore slim to control the floodgate and can control the concurrency per process. And then we have tighter control over the runtime behavior of the pump. And that worked really nicely. It was humming along in production, and we never had really big issues. Unfortunately, you probably know that as well, right? It's like as time passes, well, we can say when I was building this messaging abstraction, where I was tasked to do so, building this abstraction was a really, really fun exercise, right? It was so cool because I could distract myself from writing the infrastructure code. I could distract myself by writing infrastructure code instead of fiddling around with these damn business requirements. And I had this basically Mercedes-Benz in my mind. Well, nowadays you should probably say Tesla Model 3 or whatever, right? Because old rusty gas oil machines are no longer relevant. So let's say the Tesla Model 3 in mind. But I was the team lead, right, who originally built this abstraction. And some of my colleagues had to start maintaining the things as well because I didn't really have time anymore to really maintain it. So they started extending the code under pressure. And yeah, you get it. I'm actually claiming it's all my team's fault. No, I'm kidding. Of course I'm not. But you know it is, right? I mean, at some point you have to move on. You have to write more business code because that's where you make the money. You're not making the money unless you are in that business, but you're not making the money with infrastructure code. You're making the money by fulfilling the business requirements of your system. And over time, what you also had is we had more and more requirements that the pump needed to fulfill. So for example, we had requirements like, okay, whenever a message was successfully handled, we want to audit the message that was processed. We want to log it and everything like that. So we started extending it even more and more. We started to make it flextensible, like I say, flexible and extensible, right? So, and this is how the pump potentially really looked like. So at first sight, it doesn't really look that more complicated, but there is this fetch and handle and release with middleware. What the heck is this? So let's dive into it a little bit. So we can see here this code. What we have is in the fetch and handle and release middleware, we have like, okay, we're creating a transaction because we actually found out that it's probably beneficial to have transactions that are wrapping at least a queue, potentially even distributed transaction if you're using something on premise together with SQL Server. And then we also realized, well, we're not just calling static functions, we're actually calling stuff that needs to have dependency injection available. And we want to be able to create a new instance of something that is scoped to the lifetime of the message. Therefore, we need to create a child service provider. And then we also realized that, well, we don't want to like hard code some of the cross-cutting concerns everywhere. We actually want to solve it in a centralized way so that other developers that are using the system don't need to explicitly write that code anymore, like the auditing, the logging, and stuff like that. So we wrote this really complex func handler context cancellation token task cancellation token task kind of middleware. Oh my God, yes. So that we can actually plug in stuff into the middleware and have sort of a pipeline kind of model to extend it. And then we needed to get access to the child service provider to resolve the message handling infrastructure so that we could then actually handle the message. And we also put an abstraction in place that we called I handle messages that could handle a message of T to actually just be able to focus on the business code, right? As you can see, it's like, okay, well, this piece of code got increasingly complex over time, and we haven't even looked into the sending parts yet. So the interesting part is, depending to whom you talk to in the team, for some, it really looked like an old and rusty car, because the people that knew how we could have built it, how we could have made it fancy over time if we had the time and didn't need to focus on the business requirement, for them it was like an old and rusty car, and said, yeah, it's going to break apart, and parts will fall off because it's so rusty, right? And for some others that we don't really liked it or even didn't really want to touch it, it looked like this crappy banana car. And by the way, that happens when you're procrastinating over a talk and you start Googling for funny car pictures, then you find banana cars. Don't ask me how I ended up there, honestly. Okay, but for some people, that's like, oh, this is nice, this is fancy, it really looked like this, right? Whenever I look at this picture, I'm like, okay, that's funny. It's like, how did the guy build this car? And he was like super excited. And his girlfriend looks like, yeah, I don't know what I'm doing here. It's kind of embarrassing. Anyway, that's probably the feeling that some of my team members had as well. Good. But now we actually have talked about the basic bits, about the sending and receiving, as well as a little bit of transaction handling that I showed in how the pump really looked like. But once we have to actually build reliable and robust middleware code, we also have to have a deeper look at transactions, and we want to at least think about transactions. So what we can say is the code that is executed under a message being received is never side effect free, right? So as part of the code, you might send out other messages or you save some state into the database. So with on premises with MSMQ and SQL Server, if you know what you're doing, the transaction can automatically enlist with this distributed transaction coordinator under a transaction scope. So what we can say is when the pump starts the transaction, it fetches messages from the queue, fetches the message, executes the code, and then it sends the messages as a transaction to the destination and also operates on the storage. And if everything was successful, it then commits, or in the non-successful case, it aborts the transaction. And this piece of code, like I said, with for example, SQL Server and MSMQ on premises, it can actually enlist into what is so-called distributed transaction coordinator if it's being run under its transaction scope. So that means both the sending messages and the manipulating data are guaranteed to be executed eventually as a whole or rolled back as a whole. So the way that you structure your code and your sends and your publishes with the data access doesn't really matter. In some regards, if you don't have the distributed transaction coordinator, but you're using the same system to store your messages as well as storing your business data. For example, you could imagine yourself doing queuing over SQL Server. Then you're storing the messages for the queues in SQL Server as well as your business data in the SQL Server. Then you don't need distributed transactions. What you then need to do is you need a way to share the transaction that is spawned by the message pump to receive the message from the queue with all your business code, so that all the business operations that you're executing against the SQL Server are participating in the same transaction, so that if something goes wrong, the transaction is rolled back, and then that means the message is back into the queue and no business operation rights have occurred, right? So if you need more the problem is that with the distributed transaction coordinator, and sometimes also with transaction sharing, these operations can be quite costly. It's extremely costly with the distributed transaction in place, because that two-phase commit protocol has a high overhead, and your throughput can actually fall down by an order of magnitude. So if you need more throughput, for example, on premises, you might want to move to RabbitMQ, right? From maybe MSMQ to RabbitMQ. And so at that point, you're not only throwing away all the underlying plumbing code, but your move to this different technology also has a larger implications on how you write your code and how your code might behave at runtime. So what we can say is RabbitMQ doesn't provide what is called cross-queue transactions. It only supports what we call receive-only transaction. So in this mode, in the receive-only transaction mode, the receive operation is wrapped in a transport native transaction. The native transaction is implemented by either ACKing or NACKing the message depending on the outcome that you want to achieve. So this mode guarantees that the message is not permanently deleted from the incoming queue until at least one processing attempt, including storing user data and sending out messages, is finished successfully. So in this mode, some or all the handlers might get invoked multiple times, and partial results might be visible. So we have the concept of partial updates, where one handler succeeds updating the data, but others didn't. And we can see it here illustrated in this picture. What we can see is, if as part of the message handling infrastructure, we're executing two pieces of code concurrently, two handlers, so to speak. One is successful and successfully writes into the database. The other one failed. It failed to write to the destination. It also failed to write to the storage. Once the message is nacked on RabbitMQ and rolled back, or any transport that only supports receive-only transaction, what it means is the successful handler update on the storage will still be written. The side effects of the red handler will be rolled back, potentially by accident. But we can essentially get any in-between states of partial updates visible in the system. But there is also what I call the partial sends, where some of the messages have been sent and others don't. So what it means is, like in the previous example, even if it's just one code, even if you're not executing concurrent code, what we can say is that, for example, we write to the database, which is successful. We write to destination 1, and then we try to write to destination 2, which might be on the same broker, but temporarily the connection might be unavailable, or it might be on a different broker that we need to connect to that has different SLAs, and then that one is down, therefore we fail to write. And then if you're not writing the code in correct way, we might miss that fact. So that means destination 1 will already have the message, but destination 2 will not, and we will also have written all the side effects into the storage. So the next time we retry that message, we again have 3 potential failure scenarios that can go wrong. So what we can say is, when we're using this mode, all handlers must be idempotent. What that means is, it's just a fancy term of saying the result needs to be consistent from a business perspective, even when the message is processed more than once. And the position of the code, where you place it, where you write the message sends, how you act the message or nack the message, has to be really precise. And if you're not putting the code into the right place, and if you forget certain scenarios, what it means is your code will not be robust anymore. And then in the worst case, because we're handling business transactions as messages, it could mean that we're losing messages. And losing messages always means, in that world, you're actually losing money because you're losing the business intent, right? So that's really crucial. But what happens if you need to move your code to the cloud because your on-premise data center is no longer cost-effective, or the new CTO of the company has this lift and shift strategy because it's the fancy word of the day to move to the cloud, or whatever logical or illogical reasons you might have to move to the cloud, right? Depending on where you go. For example, if you go to AWS SQS, it only provides receive-only transaction modes. But the transaction is implemented using a timeout mechanism called visibility time. And like the slide says, is once you're moving to the cloud, we are basically cloudy with a chance of failure. And I'm going to talk a little bit about the different things that you need to take into account if you're using cloud-based transport. Again, coming back to AWS, should you choose to go to AWS, you might stumble upon SQS, and that's a receive-only transport transaction using message visibility timeouts. What that means is, once we start handling a message for the time of the message visibility, which by default is 30 seconds, by the way, what's going to happen is the message will be not visible in the queue. Once the timeout is over, then the message is visible again. So what that means is until the processing is not done, the message and the timeout is not yet over, the message is not visible. But let's imagine our business code requires more than the previously mentioned 30 seconds. What that is going to mean is that after 30 seconds of processing the business intent will reappear in AWS SQS. Therefore, it can be picked up by the same endpoint if the endpoint has multiple concurrencies and it still has slots available in the semaphore. Or if we're doing competing consumer, having the same endpoint scaled out, it can be picked up by another endpoint, therefore completing the same business transaction potentially at the same time or in different times, but we handle it multiple times. And by the way, if you're in Azure, and using, for example, Azure Storage Queues also implements transactions with message visibility timeout. If you're in Azure and you're using Azure Service Bus, then many people don't know that the broker natively supports what we call Sense with Atomic Receive. I'm going to talk a little bit about what Sense with Atomic Receive means. Sense with Atomic Receive works with a send via header, and the transaction scope that is wrapping only the SDK operations, and they are allowed to enlist in a volatile fashion on that transaction scope. What that means is your business transaction, for example, your SQL writes, your SQL connection cannot enlist in this transaction scope. Only the Azure SDK transactions can enlist, and the transaction scope needs to spawn all the message operations. So you would need to clearly separate the message operations from the actual business rights, and you need to wrap the whole transaction scope from the SDK perspective around that code, or properly suppress it where it shouldn't be visible to the underlying, for example, SQL writes. So it's a fairly complex operation, but it is supported. And what it means is that transport actually supports that outgoing operations can enlist in the currently received transport transactions. And this prevents messages being sent to downstream endpoints during retries. Let me quickly illustrate that here on this slide. So when we start a transaction, we wrap the transaction in a transaction scope. Then we execute the code. And then the destination writes to destination 1. They're actually not done directly to the destination, but they are actually sent as a transaction attached to the currently received message into the input queue. And then the next write is also done to that input queue. And then we do our storage operations. And then once we commit a transaction, we also tell the broker, hey, we're actually done. And via that send via header, the broker actually figures out where the messages need to go and then reliably transfer the messages from the input queue to the destinations queue. Well, it's not actually the input queue, it's actually a special transfer queue, but that's details that are not that relevant. Should you be interested, feel free to give me a shout out on Twitter, and I will show you some links that you can deep dive into. So what we actually have is we have the same transactional guarantees as receive only, but in addition, it prevents occurrence of what we call ghost messages, since all outgoing operations are atomic with the ongoing receive operations. But of course, as you saw in the picture, the storage rights, they're independent from that transaction. So we're only preventing the problem of duplicated sends to destinations. So that's so far about the transactional capabilities of a transport. When our code needs to embrace the cloud or even remote resources in efficient manner, we have to take latency and bandwidth into account as well. So in the cloud, there is this term, I think it was probably coined by Scott Hanselman, but I'm not really sure. But I've heard it on a Scott Hanselman blog post a few years ago. There's this concept called penny pinching, right? Because what it matters is its cost effectiveness of the code that is running in the cloud. So every request to the broker, for example, to Azure Service Bus counts, right? Because we are actually billed by operations per second. So for example, with Azure Service Bus, the first 13 million operations per month are included, and the next 87 operations are billed by, I think, roughly 80 cents, US dollar cents per million operations. And that sounds like an awful lot of requests that we can make against Azure Service Bus. After all, 13 or 87 millions is a huge number, isn't it? Right? Well, if you do the math and just assume that you have 87 million operations, it roughly boils down to 120 requests per hour. And that's not much, considering that every receive operation against Azure Service Bus is one operation. And every send also counts as one operation. And for Azure Service Bus, we're also getting charged by the number of AMQP connections. And the first 1,000 connections per month are included on the standard tier. And after that, we're getting charged by I think, roughly 3 cents US dollars per connection per month. So we need to take that into account. But things are getting worse. Let's say, considering your code sends a message out, for example, in a for each loop, after a message was received. If you do the naive approach, every send operation is an operation against the broker. So in order to maximize the cost savings and reduce the latency that we have between our code even if it's running in the same data center, there will be latency. If it's running outside the data center, then it's even worse, right? Because the latency between where your code is running to your closest data center is going to be in the order of tens of milliseconds, unless you're buying a dedicated lane to the data center. But then we're talking also about different costs being involved. And that also the latency is not fixed, right? It might depend depending on the other traffic that is going on the connection towards the data center. So it might, for every request, it can actually be different. So in order to deal with that, in order to maximize the cost savings, what you have to do is we have to put as much as we can into one single call. And batching is a concept that we can apply here. By the way, and batching also helps to deal with what I previously called ghost messages, because we batch more requests into a single request, but that's a topic of another talk. Let's have a look at how batching actually can be applied. So I hand-waved a little bit this batching concept on the previous slide and talked about latency and operation costs, but and I said as much as we can batch into a single request or in a single call. Unfortunately, every transport has different constraints when it comes to how much data you can put into a single call. So for example, with Azure Service Bus, depending on the tier, can batch up to 256 kilobyte data in the standard tier. I think at the premium tier, it's roughly 1 megabyte of data. With AWS SQS, it's also 256 kilobyte with storage queues, although it's only 64 kilobyte. With RabbitMQ, especially on premises, you can shuffle as much data as you want, but you are actually limiting your throughput because you're actually, the more you batch into a single call, the more memory RabbitMQ requires, the more resources, which has an effect on that broker and all the connected clients. So you need to be smart about those decisions as well. But what you're faced with is you actually need to write smart batching logic that figures out the payload, headers and the body, and how much data can be put into a single call while still being able to keep all the transactional guarantees, right? Plus, you have to deal with the SDK and broker depending behavior. So for example, here, what we can say is if you have 256 kilobyte and we have pretty large messages, we might be able to have 2 messages in one batch, 256 kilobytes, and then potentially 5 other messages in the second batch and 2 other messages in the third batch. So we need to dynamically allocate messages that we're sending as part of the same batch, so that we are still complying with the broker's needs. And again, for example, if you send with atomic receive with Azure Service Bus, what you also have to do is you can only batch things together that go to the same destination. So that means if you're sending out multiple messages to destination 1 and destination 2, you can only have in a single batch operations that are going to destination 1, and in another batch all operations that are going to destination 2. And of course, those batches need also to be subdivided depending on the size of the messages. With AWS SQS, what's worse is that, for example, you can send batches of individual messages, but then the broker tells you that some individual messages within that batch actually failed, and then you have to retry those individual messages. So pretty fun times. So now we have the basic bits. We have the basic building blocks of sending, receiving, dealing with transactions, and also smart batching to do the necessary penny pinching in the cloud, so that you can build your own robust and reliable message pump. But as we know, when our software grows, the demand that we have on that infrastructure, library, and framework, that grows as well. So basically, we're living on the edge of sanity. So, because what about if we, for example, need to do delayed delivery? So, for example, we want to leverage the queuing technology to send messages into the future, or to apply back pressure when we can't handle it. For example, we're saying, let me give that message back in 30 seconds. Then we also want to do scaled out competing consumers on the same queue. We need to manage the state, for example, of the things that are going on. We need to adjust the runtime information like routing, depending on the topology that we're using. We need to think about the topology because, for example, Azure Service Bus has concepts like topics, subscriptions, and queues. And we need to think about what is a topic, how does it map to queues, how do we use subscriptions, where do we receive from, on all that kind of decisions we need to make. And there is also the human factors that go beyond the code. So, for example, who is going to write documentation? Do we have time to write documentation? How do you teach new developers that are joining the team how the system works and how it can be evolved? And what happens if you, the mastermind who wrote that code, leaves the team? But that's only the tip of the iceberg, because once we are relying on that library that we wrote, we're leveraging this distributed system, we most of the time also have a distributed systems mess, right? Because how do we know what's going on in the system? How do we troubleshoot it? How do we monitor it? How do we visualize what's going on? And how do we determine whether the consumers that we have in place can still cope with the load that we currently have on the queues? And once it's in production, and for example, the CEO just acquired a new company, and the CEO comes to your team and asks them, well, we just acquired this company. Can the system handle this load? Or if you have an outage in production, we have no insights, then we are pretty much flying blind. So what we can say is these distributed systems, they are pretty complex, and there is no denying that. So you need proper tooling to make sure everything is running properly and to get insights into the system. And using a monitoring system is not too hard. Setting up all the hooks in the middleware might be non-trivial though. So of course you can then, once you have set up that in the middleware, you can start shipping the data to things like application insights, Grafana, Prometheus, or whatever fancy tool of the day that you think you need to be using, so that you're getting insights into what is running in the system, like visualizing the routes that the messages are taking, visualizing the critical time that we talked about, the processing time that we talked about, the number of retries going on in the system, the failure rates, and so on. Good. Well, to wrap things up, I really strongly encourage you to try this yourself on a personal project or a small part of your work project. I mean, I believe that knowing the inner workings of a message pump is highly valuable, even if you don't end up using it in production. Because I think being armed with this knowledge that I just gave you, it helps you to make the right trade-offs in your project when it comes to make or buy decisions. That's all. Thank you very much for listening. It was a pleasure for me to talk to you. The slides, you can find them on github.com/DanielMarbach/message pump. And we also, a few details about me, should you wish to get in contact with me. My name is Daniel Marbach. Again, I work for Particular Software. You find me on Twitter under @DanielMarbach. You can also find me at daniel.marbach@particular.net should you wish to send me an email. You'll find me blogging under planetgeek.ch. And thank you very much again. And I wish you a great rest of your day.